Hey everyone, and welcome back to This Explainer. Today we're diving into a truly fascinating programming challenge. We're looking at how to use Haskell, a functional programming language, to mathematically transform Chinese numerals right into full-width Arabic digits. You know, when we read a number like 300, our brains just get it, right? It's effortless. But trying to teach a computer to understand that text, that requires breaking down these deep, almost invisible linguistic rules and translating them into hard, undeniable logic. So we're going to look at a developer's real-world code to see exactly how they bridge this crazy gap between human language and elegant software architecture. Let's get into it. Okay, here's our roadmap for today. We'll start with the numeral conversion setup, then check out Haskell guards and routing, move on to parsing the actual Chinese numerals, and finally, calculate with multipliers. So, part 1, the numeral conversion setup. Right, so our main goal here is pretty straightforward, but completely foundational. We want to take textual Chinese numbers and format them into full-width numerical digits. You know, those wider digits you often see in East Asian typography. But before we even touch the Chinese characters, we need a baseline. The authors set up an explicit mapping function that literally just flips standard single-width ASCII digits, your everyday 0 through 9, into their full-width equivalents. And what's absolutely crucial about this explicit mapping is how safe it is. By spelling it out character by character, the developer creates this incredibly strict set of rules. Any non-numeric character, it just gets caught by a catch-all case and passed right on through, totally unaltered. Imagine feeding like a massive 10,000-word document into this. You only want the numbers changed, right? Every comma, period, or letter needs to be completely untouched. It's just a simple, rock-solid baseline to build on. Moving right along to part 2, Haskell guards and routing. Now, to avoid ending up with this messy alphabet soup of code, the developer points out a really cool advantage Haskell has over languages like Elixir. In a lot of programming languages, if you want to handle different kinds of text inputs, you usually have to write multiple separate functions using a technique called pattern matching. Basically, you're creating a new set of instructions for every single possible variation, which, yep, it can get incredibly bloated really fast. But Haskell totally bypasses that. It uses these pipe characters, they're called guards, which support complex, custom Boolean expressions. It's like building a super smart, multi-lane sorting mechanism. It keeps all the routing logic incredibly clean, super readable, and totally centralized right in one elegant block of code. Think of this dispatcher as a highly efficient traffic cop. It evaluates the incoming text against 4 custom Boolean pipelines. First up, if the text is completely empty, say a chapter header without a number, it just cleanly returns nothing and stops the operation right there. Second, if the text is just standard single-width digits, our traffic cop routes it straight to the mapping function we literally just talked about. Third, if it's already formatted as full-width digits, boom, it just passes it right back, no wasted computing power. But the fourth condition, this is the masterstroke. If the input is none of those things, the program just assumes, okay, we're dealing with Chinese numerals, and seamlessly routes that text directly into our core mathematical calculation function. Which brings us to part 3, parsing Chinese numerals. Okay, here is the real plot twist of this whole explainer. Standard programming languages, they are built by and for Western mathematical paradigms. We can't just do a simple one-to-one character swap anymore, guys. We essentially have to teach our Haskell code the rules of an entirely different language system. The absolutely crucial point here is figuring out how to translate Chinese characters that just flat out do not mathematically behave like Western numbers. We are literally standing right at the intersection of computer science and linguistics. The core of this challenge really comes down to the difference between these two systems. Unlike Western Arabic numbers that rely strictly on a positional place value system, Chinese numerals use a positional multiplier system. So let's break that down for a second. In the West, if you write the number 5,000, the 5 means 5,000 simply because of where it sits relative to the 3 zeros following it, right? The value is totally implied by its position. But in Chinese, you write it with 2 characters, which literally translates to the character for 5, followed by the explicit character for 1,000. This fundamental difference completely changes how we have to code the math. We're no longer just looking at a string of digits, we're looking at specific numbers and the explicit linguistic rules for multiplying them together. And that takes us to our final section, part 4, calculating with multipliers. To solve this massive architectural difference, the author brings in a classic programming concept, a finite state machine. Just picture a finite state machine as a little memory box that updates its contents with every single new character it reads. To run this machine, the program uses a really powerful Haskell function called fold left prime. It evaluates our Chinese characters one at a time, moving strictly left to right, and calculating a running state inside that memory box as it goes. And here's the best part, it is intentionally incredibly strict. If the loop hits an invalid character, like a typo or some unknown unit, the whole operation fails immediately and just returns nothing. In functional programming, failing fast like this, that's actually a fantastic feature, not a bug. It makes sure bad data doesn't accidentally get calculated into just total nonsense. Now, alongside standard digits 0 through 9, our little state machine has to process two very distinct types of multipliers that actually dictate the mathematical rules of the string. First, we have positional multipliers. These represent the smaller standard values, like 10, 100, or 1,000. And then we have magnitude multipliers. These represent those massive jumps, like 10,000 or 100 million. The sheer elegance of this code is how perfectly it categorizes these two behaviors, applying distinctly different mathematical logic depending on exactly which type of multiplier the state machine hits. Let's actually look at a step-by-step trace of a positional multiplier in action. We'll use the text for 33, which translates literally to 310-3. So step 1, our memory box starts with an initial state of 0, 0. It's basically a two-part slot holding our current multiplier state and our running total. Step 2, it reads the character for 3, holding that value in memory. Step 3, it hits the positional multiplier for 10, so it immediately multiplies that previous 3 by 10 to get 30. And finally, step 4, it reads the last character for 3, adds it to the 30, and correctly outputs the final number, 33. The computer successfully read the text sequentially and turned it into perfect math. Pretty cool, right? But magnitude multipliers, they are an entirely different beast. And this is where the state machine's design absolutely shines. Take the text for 120,000. The machine starts by reading 10, then it adds 2, making 12. But in step 3, when it hits the magnitude multiplier for 10,000, it doesn't just multiply that previous digit. No way. It reaches back and applies to the entire sum that preceded it. It takes that whole 12, multiplies it by 10,000, and outputs 120,000. I mean, this is the absolute aha moment of the code. It flawlessly mimics the actual cognitive rules of the human language. This algorithmic mapping of language is just undeniably fascinating. You start to realize code isn't just about raw math. It's about translating human thought and these deep cultural structures into a format that a machine can execute seamlessly. We basically took a human linguistic structure and perfectly recreated its rules using Haskell's guards, fold-left functions, and finite state machines. And it really leaves you wondering, doesn't it? What other invisible linguistic paradigms are out there, just waiting to challenge our programming logic and be solved by an elegant piece of code? Thanks for joining me on this explainer today. Keep learning, keep questioning, and I'll catch you next time.